CLion a cross-platform IDE for C and C++. Download now.
So welcome everyone. Thank you for joining this talk where we are going to talk about whether clean code leads to horrible performance. But before we get into the details, let me quickly introduce myself. My name is Sandor DARGO. I work for Spotify, and I spend most of my free time either reading or writing, mostly not only about C++. It especially changed during the last year or so. I started to learn more about winemaking and wines, and I'm writing about French wine sometimes, as I live in France, for some Hungarian online portals. But well, that's mostly enough about myself. Let me quickly talk you through why I made this talk. So in 2023, about 2 years ago, I gave a talk at C++ on C with the title, Why Clean Code is Not the Norm. And it led to some interesting discussions, either on site and also later virtually. People shared some interesting videos, articles, and we kept discussing. And I realized once again that many people think that things are either black or white. They talk about things in absolutes, and I don't really like that. I think life is more nuanced than that, and especially engineering is more nuanced than that. And most often we cannot just say that, okay, this is bad, this is good, this will fix everything, or this will ruin everything. I think things don't work like that. So these inspired this talk, and we are going to see the agenda now. So first, we are going to define what's clean code. Then we'll see what is software quality. We'll try to define what's software quality. Then this will be the sole part where I will mention C++. I think this is the only part, yes. We'll just discuss quickly where and why do we use C++? How does it fit here? What is software performance? We try to address also if finally is clean code actually slower, and if we should drop clean code or faster code. And whether we should or should not, we still have the question if clean code implies not just worse, but horrible performance. So this is what we are going to talk about in the next hour or so. Let's start with what is clean code? Well, that's not an easy thing to answer. So first, let me talk about what is not clean code. It's definitely, well, for me, it's not a closed set of rules. And here I have to mention that though I think that Uncle Bob's book is very useful, it's a great book, but when I talk about clean code in this talk, I'm not talking about the book, clean code title case. I talk about the concept of clean code. That's why I try to use it in lowercase everywhere. So it's not about the book. It's about the concept of clean code, which I think it depends on the language. So for example, if you take some C++ code that you consider clean, whatever clean it is, and you just, do your best and move it to, let's say, you translate it to Python. Most probably, it won't be that clean in Python because if you just translate it without too much thinking, and clean and idiomatic C++ code will not translate to clean and idiomatic Python code. So it does depend on the language, in my opinion, but it also depends on the context. Maybe something that you consider clean in, let's say, embedded, will not be considered clean in some other areas of C++ development. And it also changes over time. So just think about how much C++ changed during the last decade. Think about, I don't know, think about concepts, think about move semantics, think about how much more functional programming constructs we get into C++ and how much we like to use them. And something that we consider clean C++ maybe like 15 years ago, probably you would say that it's not the cleanest you can imagine now. So it does change over time, but it's certainly clean code is certainly not a silver bullet that will address all your problems or something that will cause all your troubles either. So clean code is not a closed set of rules, but then what is clean code? To talk more in about positive way. Well, if I have to take one phrase that defines it, this is my favorite. Clean code is code that's easy to understand and easy to change. So let's break down the easy to understand part. What should be easy to understand? Well, definitely the execution flow. Also, the relationship between different objects. But we have to get deeper than that. We have the roles and responsibilities of these entities have to be easy to understand, and also the purpose of each and every expression, if you want something that's very clean. Now there's the other side. Should be easy to change. But when code is easy to change, well, there are a few parts here as well. Classes should have concise public interfaces. And these classes should be easily testable, but it's not enough that they are easily testable. They should also have the tests. Tests should be there. And the entities should be predictable and work as expected. Now, I don't know, you might think that this is granted, but well, during well, it's definitely not. It's definitely not. I don't want to bring very specific examples from my last few months. The entities should be small and they should bear only one single responsibility. Then it's easy to change. Otherwise, not so much. I say that clean code is part of software quality. The question is high quality software important at all? I say that obviously, but I remember having discussions in the past, it's a long time ago, maybe 6-7 years ago in a previous thing, when people said, we don't think that clean code, we don't think that high quality software is really important because our customers, they don't care. Well, we'll discuss about this, and I think that indirectly they would. But it's true that quality isn't so important all the time. For example, when you just build a proof of concept, or you're in a startup still searching the product market fit, or you just must deliver something to survive, probably quality is not the first thing that you will think about. But what if you plan for a longer term? Well, then quality, software quality, high quality software becomes much, much more important. But if we talk about quality, we have to define what software quality. And maybe, just maybe, it would be easier to define first what quality is, if we want to define software quality. Well, the thing is that people who are way smarter than me, they spent decades, if not lifetimes, searching the answer what quality is. And they wrote books about it and whatever. And the thing is, it's very hard to define quality, if not impossible. So some people say that quality is in fact undefinable, but you will recognize it when you see it. But let's probably not a good enough answer for us. So we have to get back to software quality and try to define it. Well, if you look around on the internet, on Wikipedia, whatever, you will see that there are plenty of different definitions, dozens, and they take different approaches. And one might even say, and one definitely says so, that it's just a meaningless term. Software quality can be interpreted as a meaningless term because it means so many different things to different people. And in fact, it was Derek Jones in the era of software quality who said so. It's people in industry are very interested in software quality, and sometimes they have the confusing experience of talking to me about it. My first response on being asked about software quality is to ask what the questioner means by software quality. After letting them fumble for about 10 seconds or so, trying to articulate an answer, I offer several possibilities, which they are often not happy with. Then I explain how software quality is a meaningless marketing term. This leaves them confused and unhappy. People have a yearning for software quality, which makes them easy prey for the snake or salesman. Well, fair enough. Can mean different things, and it can remove the meaning. But I still think that in order to move here forward, we have to pick a definition. And I picked the one from the Consortium for Information and Software Quality. They take 4 pillars defining structural software quality. So this is even more a bit more specified, not simply software quality, but structural quality of software. So these 4 pillars are security, reliability, maintainability, and performance efficiency. Now, let's have a look at these. How clean code is part of software quality. First of all, I think that clean code helps reducing the number of bugs. Well, that's one of the goals, right? So it improves the security, less bugs, probably more security that we have. It improves also the reliability and the maintainability of software. That's good. Now it also helps reducing the time to fix bugs, which in my opinion improves the reliability because in the same amount of time you will be able to fix more bugs, but you have less of them in any case. But even if you argue that, I think we can all agree that if we have if we can fix bugs in less time, then the maintainability of the software is improved. And therefore, clean code decreases maintenance costs over the long term. But it's very good because if we look back at the 4 pillars of structural quality, we covered security, we covered reliability, and we also covered maintainability. That's already 3 out of 4. But what about performance efficiency? We didn't talk about performance. And well, if you want to talk about performance, sorry, it's not going to happen right now. We make a small detour to the world of C++, and we'll cover where and why do we use C++. So first, let's see, hey, where is C++ used? Well, probably we are all aware that our probably favorite language is just everywhere. It's in our mobile phones, it's in household appliances, in our cars, airplanes, photo editing software, 3D and not 3D games. It's in browsers and compilers, enterprise software, financial software, and of course, in our favorite music app in Spotify. We are also heavy users of C++. Okay, it's everywhere. Why? Why do we use C++? Well, the first answer that's probably don't leave you very happy is that it's because it's legacy, right? It's been with us since the 80s, and we have millions, if not billions, of lines of often complex and critical existing code. And at some conference recently, I heard the number, an estimation of how much money it would take to rewrite all that code. I don't remember the number, but it it's extraordinary. And you know, partly because of that, partly because of the money, rewrites rarely make sense, even if C++ is not needed for the domain. I definitely worked on software in the past where, you know, when they started to write it in the 90s, probably C++ was the best option. Maybe it's not really needed nowadays, but it's kind of out of question to move away. And well, I'm not saying that's bad. It's just bad or good. It's just a fact. Because one thing that it would be a loss of time. And developing software in parallel, well, okay, that's difficult. Doing a big bang would be also a big bang of migration would be very difficult as well. But there is also the problem of existing ecosystem, and I'm not talking about you know the C++ community and what kind of software softwares there are that help us to write better C++. I talk about company specific ecosystems because, well, in C++, we often, lack some standardized tooling around C++. So companies took time and money to develop their own build systems, whatever. And well, you would lose that one as well. But it's not the worst. You would lose so much knowledge because there are people out there developers out there who think that, okay, I like this company or whatever, and I'm just happy to write code in whatever language I'll learn another, and yeah, of course we can rewrite. But many developers, and I think especially C or C++ developers, uh, they, I don't want that. We don't want to move to another language. So we'll live with the knowledge. And I'm not talking about the knowledge of C++. I'm talking about the business knowledge. And that would be a problem for many companies if they decided to rewrite their C++ systems in another language. But C++ is not simply legacy. It's an evolving language. Especially, okay, the first 2, 3 decades were probably quite slow in terms of development, but since C++11, we have a stable and steady evolution, and every 3 years, we get a new standard. We get bug fixes, we get new language features, we get new library features, and it's definitely moving forward. Now, I know that some of you would say that, well, it's moving too slow, but there are others who say that, well, it's moving too fast. What we agree on is that it's moving. That's moving forward. So it's an evolving language. And we get safer and more expressive code with each and every standard. And that's a good thing. And also, it's not owned by a single corporation, which is probably a positive thing for uh, for many of us. So that's good. But this is not the only reason. Okay, these are not the only reasons why we are still using C++. Yes, legacy. Yes, evolving. But it has some very important advantages, and that's an economic advantage. Maybe you already read about some research where they measured energy, time, and memory efficiency of different languages, and you can see on these charts that C, along with some other languages like mostly C++, along with C and Rust, they they are among the most efficient languages. Well, one might say that, well, okay, I see that O.3 or O.5 difference in terms of energy or time consumption, but That's a really small difference. If you check, for example, the time efficiency between, let's say, C and Python, which is on a different scale than the differences between, let's say, Rust and C++. So C++ is definitely a fast language, and it's good for performance critical applications. And it also uses little space in terms of binary, but it also uses little memory. And that's good for the embedded world or for anything that has to be distributed over the network. For example, for us in Spotify, binary size is something very important. We'll talk about that a bit later. And it also consumes, C++ consumes less energy, and that's just great for everyone. So in one word, C++ is performant. C++ is among the most performant languages. And that's such an economic advantage that really often justifies its usage. But I throw in a word, performant. Okay, C++ is performant, but what is software performance? Especially if we want to define, the relationship between. We want to dig into the relationship between clean code and software performance. We have to try to understand what software performance is from a practical point of view. So again, this is something that's very difficult to define, but we can agree on that performance is a non-functional characteristic of software. And often, more often than not, it's not just a characteristic, it's a non-functional requirement as well. One could say it's a metric of efficiency. Now, if we want to be able to talk about it, well, we should still try to make it into one phrase, even if it's what we said for the time being, it's like quality. It's not really specific as a term. So what we can say is that sufficient performance ensures that the software can achieve its functional requirements in a reasonable time span. Emphasis on reasonable. Okay, what's reasonable? That's question. Okay, that's very vague, right? So let's see some different aspects of software performance to see how difficult it is to define or talk about performance. Here are some different aspects. One is response time. Like, okay, you do something on the software, how fast will it respond to the user? Another aspect, the throughput, how many requests it can handle simultaneously. But we could also discuss about resource utilization, like how efficiently it uses system resources. Those can be quite different. Or scalability, which is the ability to maintain performance levels as the workload increases. See, it doesn't talk about runtime performance, for example, as something that we like to talk about. Or another aspect, there's capacity, the maximum load or number of users before severe performance degradation, which is not the same as scalability, but we can also discuss about stability, which is another aspect of performance. So over time, how it can perform without crashes, memory leaks, or some other issues. I'll bring some example about that. And we haven't mentioned runtime performance, but when we talk about software performance, especially C++ developers, often we talk about runtime performance, but we just saw like half a dozen different aspects that might not be the same as runtime performance. Is it the same as execution speed? It's mostly, I think the runtime performance is mostly about execution speed. And, it's not only about algorithmic complexity, something that we love to discuss, even you go to an interview. And they ask, okay, what's the algorithmic complexity of this piece of code? Like, as if that was the most important thing. Well, because they analyze that, okay, to analyze runtime performance, well, or understand runtime performance, execution speed, well, language is important. That we already saw from that chart before. And the layers of abstractions can also matter a lot. It's not simply about algorithmic complexity. If these other things, well, in fact, if any of these are neglected, uh, and if runtime performance in general is neglected, other aspects will also suffer. Sure, sure, but this is not the sole most important thing, I think. There are other kinds of performance we have to care about, like load performance, reliability, scalability, efficiency. The startup time of some software can be critical. After all this, can we say that clean code is slower? Is clean code actually slower? I'd say that clean code is actually slower than what? We need a basis for comparison, right? We cannot just say that clean code is slower. Of course, yeah, why not? But slower than what? Uh, there was a German philosopher called, I think, Gottfried Leibniz, and he famously said that, well, he wrote that, well, we live in the best of all possible worlds. I don't know if he was right or not, but I know that clean code is not the fastest of all possible codes. It's for sure. And the reason is that clean code is just an optimization. It's an optimization for maintainability. Therefore, it's not the most efficient or fastest code, for sure. It's not the shortest code either. It's not the code that will lead to the smallest binary size either. But the question is, will it hurt performance, or is it an acceptable compromise? Because optimization is always about compromises. No matter what you optimize for. You can optimize for runtime performance, for any kind of performance. You will definitely hurt the readability of your code. You go to any C++ conference, and I think if you go to lightning talks, you will definitely see people talking about how they optimized, I don't know, printing something, and it prints things, I don't know, 1,000 times faster than you would print with the standard library. And it's always stellar code. Okay, it's very interesting. I wouldn't be able to do that. And I really appreciate these talks. But what we can also agree that it's an optimization, and it's not readable code. So you optimize for performance, you hurt readability, and probably you will hurt binary size as well, and you might hurt even portability. You optimize for binary size, it's similar. You might hurt the readability, and you might even hurt portability of your code, but if that's what you have to optimize for, probably, or maybe, it's an acceptable compromise. Just like you will hurt runtime performance. In some cases, okay, you might. But when you optimize for readability, you'll hurt runtime performance, for sure. And you will hurt binary size as well. But that's why we talk about optimization. Now the question is, should we drop clean code for faster code? Well, the answer is it depends. sometimes every bit of performance matters. I gathered some pieces of information from here and there, and maybe the numbers are not correct anymore, but they definitely give you the impression how and why these things matter. So uh, somewhere they said that every tenth of a second of latency costs 1% in sales for Amazon. Or broker could lose like $4 million per millisecond in revenue if a competitor was 5 milliseconds ahead. Or an extra half second in search page generation can drop Google's traffic by 20%. Akamai found that every tenth of a second delay in a website load time drops the conversion rate by 7%. These cases, we talk about serious money, and maybe in these cases, uh, maintainability will not be your most important problem, because you don't want to lose all that money, all that revenue. If I think about Spotify, I have to say that performance is crucial for us as well. When you open the application, startup time is really important. When you start playing a track, it's very important for us that you start listening to your content as soon as possible, or when just tap on a button. You must get the feedback immediately. But otherwise, there are more important aspects, like small binary, because we do have to think about people who live in markets or in regions where network bandwidth is not so abundant. They still have to be able to download as soon as possible, as fast as possible, the app. And the code has to be maintainable. Like there are thousands of developers working on it, and there are bugs, there are new features. Well, if it's not maintainable, then this becomes hell. But what I have to say that even when performance matters, the first answer is not low-level code optimization, as otherwise it's sometimes suggested by people. So let me give you a few examples. The first one is it's about partly about algorithmic complexity. And I'm saying that it's not necessarily so important. So there was my first project as a C++ engineer, and I think it was very well. It went in very bad directions in many different ways. But I by the time I created pull request, probably months passed, and it was very big and very bad. But if you raise something huge, then you won't get so many comments as if you raise a pull request with 10 lines, when I will get tons of comments. Well, it got merged. It was slow. It also had an immense memory leak. Well, what do you think? What's worse? Was it the speed or the operability issue that posed the bigger problem? I think that there were some people there who thought that, oh, okay, it's the speed. They were more concerned by the speed. Before let's say converting into a software developer, I was working in operations. I was a database admin, and for me, therefore, I was working in operations before. Operability was a more important problem. But I was not among probably the loudest people there, and some people said that, oh, okay, you wrote that algorithm. That's horrible. It's like a for loop in a for loop in a for loop in a for loop. It was that bad. was that bad. It was horrible. But, well, I did my best at that time. We all improved. And said, okay, that must be the problem. I wasn't really bothered by that piece of horrible code, but I wanted to reply somehow, like, okay, let's not waste time on this. So I didn't know how to really to measure runtime performance, or how to measure the performance of software where we spend time. So I checked the logs. I took a spreadsheet. I put there some numbers, and I said, well, okay, it just takes it took a fraction of the execution time. It's not the problem. Well, it's bad code for sure, but that's not the problem. But this already leads to 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 a law that a guy named Amdal said. He said that the overall performance improvement gained by optimizing a single part of a system is limited by the fraction of time that the improved part is actually used. That's what Amdal's law said. And that's what we face there as well. We could have optimized that piece of code, but, well, we wouldn't have gained a lot. Meaning also that, well, you can often ignore slow code if it's not on the hot path. In this case, the key was how we used a third-party library properly. Maybe it's better to see how I used that library. It was some XML handling library, and the startup cleanup functions were called more often than needed. And what Andrei wrote on Discord, yes, speed issue may actually be caused by memory leak. Yeah, it was related to this. So calling these startup and cleanup functions at the right time, they solved both issues. They solved both the speed and the memory issues. And, well, guess what? Reading documentation using libraries as they are intended is more important than writing fast code. Well, who would have those, right? Well, nevertheless, it was a nice lesson more than 10 years ago. Now let's jump a few years. And I want to talk about another project where we got some new customers, and we know that we had to support traffic growth of like 15 times. So I think we moved from a few hundred transactions per second to a few thousand transactions per second. Now, what did we have to do to support that traffic? So we didn't make the code faster. I don't remember that we made real like any such change. We had to make our systems more scalable. We had to improve operability. We had to improve resource utilization and fine-tune some network settings. And I'll get to a bit of the details here. So what did it mean to improve operability? Core services suffered from lots of memory leaks, and we had to track those down because, well, if we had much bigger traffic, meant that we stepped on these different leaky parts way more often, and the operations were quite unhappy that the servers kept running out, or they know that they would keep running out of memory if we don't fix it before the growth actually happens. So we had to track those down. We also had to fix core dumps. This meant that basically we had to remove as much undefined behavior as possible. Now again, you might say that, well, of course, it's natural. But again, I'm not talking about some fresh code or some new company there, those services were used for at least a decade before, and they were acceptable. They were not great, but they were acceptable. But with the growth, we really had to fix all these. Wouldn't incorporate. Let me check some questions in the meanwhile in Discord. So, wouldn't incorporating static analysis tools or sanitizers in code be of help in identifying these issues beforehand? Well, some of yes, you're right that it would have been better not even to introduce these problems. But we are talking about the code where some parts were 10 years old, some parts were completely new, but some parts were even 20, 25 years old. And these tools were not necessarily available at that time. And by the time we started to, for example, introduce some static code analyzer, we got so many uh, mm, so many issues that it was very difficult to fix. And it was also not a sort of like a big tech company. So you also have or tech company in a modern sense. So often you have to go to the business, say, okay, we must invest in tackling in this technical debt. And they were also not really keen to give time to that. Now, how to handle that it could be really a topic of another talk. But well, probably that's something we can discuss more on GatherTown afterwards. But for some issues, it would have helped. For some, it would have been way more difficult. But with a bit of time, we managed to fix most of the issues. Not everything, but most of it. Another thing we really had to do is consolidating external requests. Like, we can talk about the algorithmic complexity, of course, how to write faster code, but I think that optimizing network calls, DB calls that are orders of magnitude slower, that's way more important. And usually, when you want to make systems faster, this is what you have to think about first. So if you have to take these network DB calls, if you have to make them, well, check if the API offers some batching option and use that. If not, try to batch it on call side, or maybe you will have to modify the API and maybe offer your help there to make that better, so that you can make less of these calls. Or you have to think about caching, local caching of data that you want to get, and really experiment like how long you can keep those data alive on your side, and these things will help you much more than optimizing for faster code. I'd say just think about anything that will reduce the number of calls that you have to make. It will make wonders. It actually made wonders for us all these different things. And wherever I go, these things come back on different projects. I was literally reading today some architectural plans for the next years, which discuss these kind of issues. I might say that, well, we are still using C++, and we all know that there are those costly language features. What about that? Will they run? What performance? What do I talk about? Unnecessary heap allocations or copying large objects unnecessarily, using the virtual functions in vain. Well. Maybe you've seen this small comic drawing. This says that the only valid measurement of code quality is the 1 per minute. So for good code, well, you will get a few, but for bad code, you will get tons of those complaints, like, what the hell is this? And as mentioned, clean code also depends on the language. So if you want to write clean code, you probably won't have many of these costly language features in your code in any way, because this just doesn't fit clean C++ code. But in some cases, they make sense, and some usage will most probably not ruin your code. Optimization efforts have to be concentrated, because as we said with Amdahl's law, the overall performance improvement gain in a single part is very limited. If you follow general best practices, writing code, you will have a reasonable performance in most cases. So you do that, you write your code, and you follow best practices, you try to make it clean, and then you start optimizing the hot path if you need to. Otherwise, you leave the non-hot path, but even the hot path, clean, as long as you prove else. As long as you don't prove that you have to make it, you have to optimize it for runtime performance, you keep it clean. Because one thing we often forget, especially C++ developers, that performance is not larpular. It's not for itself. Performance is not for itself. But what do you see on this image? Well, there's a small piece of stone, in the tire there. That's not great. It doesn't help, right? Probably it shouldn't be there. But at the same time, there might be a bigger issue. That you don't even care about that because, well, the whole system is down. It cannot it cannot move forward at all. Now, the sad thing is that the guy who is trying to remove that small piece of stone there is often us, developers, in a code review, who care about the, like, hey, there is that extra copy over there. You shouldn't copy that string. You could avoid it. But in the same time, they don't realize that the network call is made in a loop instead of doing it once. And I'm not exaggerating here. This actually happened. We have to pay attention to what matters and not lost in these details that are indeed easier to spot. Because software engineering, in any case, is not about performance. Engineering is in the crossroads of defining and recognizing what's good enough, and stop there. Just because we can do something, just because we can write faster code, we don't have to, if it doesn't make sense. Because software engineering is not competitive programming. But why do I emphasize so much on readability? Why readability is so important? Now, let's get some numbers here. Okay, we don't need the exact numbers, but you can see here that the cost per CPU cycle over the last 50 years went down. It's cheaper and cheaper. And notice that this is a logarithmic scale there. Now, here is another chart. It's about software engineer salaries. That's going up. Okay, sadly, it's not on a logarithmic scale, but it's still going up, even if we would consider for inflation. It's going up. But at the same time, the cost per CPU clock cycle is going down. So what do we have? We have cheap and strong hardware, stronger and stronger, cheaper and cheaper, but we also have more and more expensive developers. Maybe the last 2 years was not so great, but we can't complain still. And that's why, unless truly needed, we should optimize for maintainability. So does clean code imply horrible performance? Well, sometimes. Sometimes it does, if the requirements are extreme. Maybe we all saw that video, which is about, how, I think, was it for Doom or Quake, they optimized the square root function. And then there, like, they achieved, I think, something like 20% performance gain, and it made it possible to be playable. Yes, there, clean code wouldn't have been a good option, but their requirements were extreme. In most cases, it's not. In most cases, clean code will not ruin performance, but it will give you more maintainable code. Even in the realm of C++, you know, your performance issues will come from somewhere else. It will not come from suboptimal algorithmic complexity per se. You should rather optimize how you handle your external requests and perform low-level optimizations only at a few places on the hot path if you can prove that they are needed. Otherwise, a bit worse performance and better maintainability will have a better return on investment. And that's all what I wanted to say today. Thanks a lot for being here.